My name is Zhong Lin Wang from Georgia Tech. I will give a lecture about our triboelectric nanogenerator for solar power systems and large-scale blue energy. When we talk about energy, there's a lot of approaches. Our research the last 10 years has been focused on nanoscale energy based on piezoelectric, triboelectric effect. As a result, we have to do many things. Today, we particularly talk about triboelectric nanogenerator on this branch. Triboelectricity is well known. It's about the contact electrification of two materials. When they become physical contact, charge transfer between them and remain on the surface for an extended period of time. This is known for a very long time, and each of us knows. The simple example is this glass tube with the fur rubber one against the other one, charge being produced. So this is the basic effect, that's the phenomenon. The utilization of such phenomena has been limited because this has always been treated as a negative effect in industrial production, in modern technology, because the discharge can cause damages. In our nature, many things associated with triboelectricity. Thunderstorm is an electrostatic charge in a cloud, and discharge between the earth here and the cloud give you all this thunderstorm. 1880, scientists built these Western machines, was utilized this triboelectricity, is a belt driven here. Triboelectricity can generate a voltage drop, and a discharge can happen once they build out the voltage reach a critical number. Later on, 1928, the vanograph machine was invented. This machine used the belts and carefully choose different materials that one can be positive charge, the one negative charge on the electrification here, and the belts can carry certain charges and deliver to the surface of the other spheres, and coronal discharge will deliver to the surface of larger spheres here. Okay? The negative charge given this coronal discharge to this small sphere here. So there's a voltage drop across the two spheres, and discharge can happen. This was utilized as to generate a high voltage source. So small electronics, this has not been utilized until we invented the triboelectric nanogenerator a few years ago. So when you talk about triboelectricity, it's a well-known familiar effect, but the scientific understanding remains still discovered and further studied. For example, when two materials become physical contact, charge transfer occurs. Why the charge remains on the surface and not go back when physically separate? What's the relationship between this charge with the atomic or molecular structures? What's the relationship between this charge with the surface property as we associate with? For example, surface roughness, morphology, crystal structure, many more. So this remains a field that remains to be further studied in the near future. But no one doubts the existence of triboelectricity. We use atomic force microscopy to study triboelectricity. This is an AFM tip, a metal tip, scrubbed on the silica surfaces, charge transfer can occur. By applying different bias, you can control your transfer. Positive charge, negative charge, or no charge transfer, depends on the value of the bias. This is the experimental result shows that we can apply a negative bias, we can have positive charge delivered. Or by a positive bias, we have negative charge delivered. If you turn right at a small fraction of volts, almost no charge delivered. This is manipulation of surface triboelectrification. Is interesting for understanding the fundamentals of triboelectricity. Why does this happen like this? Is related to a simple explanation. Example, this is the metal tip, plant tip, and this is the silicon surface here. The silicon surfaces have some surface states here, and partial surfaces being occupied by the electrons. And when two become physical contact, then because the occupied state here is lower the Fermi level of platinum, some of the electron will flow into a few of those states, so therefore a few up to the Fermi level of the metal, reach the balance. This was when no bias applied. But now if you apply a bias, you can manipulate the height of these states and relative to the Fermi level. If you apply a negative bias lower the surface state so that more electron flow from metal to the silicon, making the silicon negatively charged. Okay, this is a negative bias. If you put a positive bias here, then you raise the surface states here. More electron flow from the silicon back to platinum. So therefore, make the silicon positively charged here. So in such a case here, you can see that by manipulating the bias, you can either transfer different size of charge or no charge transfer occurs. So this is called manipulation of the triboelectricity on AFM tip. We can quantify the surface charge. Use a platinum tip scrubbing the surface of silicon dioxide. You can see that scrubbing the surface once, twice, 3, 4, 8 times, charge is going to deliver. So you can use a Kelvin probe microscopy to scan across. You can get a profile here. You can quantify the voltage build-up process on the surfaces. You can quantify how much was the charge density, surface charge density, how much you deliver each scanning of the tip. And this brings a lot of interest study for AFM associated techniques. In any case, we can manipulate the charge. We can introduce the charge, and this is effective. It does exist. Back to almost 5 years ago, that we have this simple experiment. 2 pieces of polymers, one attached to the other one to the similar materials. Have gold electron on top bottom. And put on finger edge. The finger motion produces an AC output. That time we produced about 3 to 5 volts, which was rather surprising for us. Later we find this triboelectricity generated powers. And we invented this extensively and invented the first triboelectric nanogenerator. Total have 4 modes. The first mode is contact separation mode. 2 material contact, triboelectricity occurs. When the physically separate a distance, this can build out a potential. This potential will be balanced by the flow of electrons. When this gap closes, the electron has to flow back to rebuild the balance. When you open again, use the force to overcome the electrostatic interaction force. Electron has to flow to balance the local field. This is cycled contact separation. Drive the electron flow in the external load back and forth, give you an AC output. So there's 2 processes occur here. Inside the circuit is triboelectrification, produce a charge and create a voltage drop. And the external load here, we can have the electrostatic induction here, the electron flow to balance the potential here. So this is the basic principle. We can use this one, generate about 200 volts, lit up many LED simultaneously. This uses organic materials, can use transparent electrode. You can make a fully transparent nanogenerator for the first time. Use organic materials. So this is the first mode, contact separation mode. The second mode is sliding mode. One material slides against the other one. Triboelectricity occurs. When a separate part, electron polarization occurs, then the electron in one electrode have to flow to balance the field on the other part. Then when closed, this field disappears, the electron flows back. This is cycle motion. Pull apart or closes, drive the electron flow in the external load is the second mode. And this one can happen in many cases. In the disc shape, can be a sliding case here. As you see here, this is how people demonstrate that this can sliding back and forth, and then you can drive the line like this. Okay. Normally, this has a high voltage output, and this is the second mode, sliding mode. The third mode is single electron mode. The single electron mode works such a way is have one part, for example, the conductor aluminum, which connects to the grounded. It's grounded. If the PDFE is sliding apart, sliding part, because this part of it is an insulator. The triboelectricity occurs here and remain on the surface. Then this part of the charge will not be balanced here, so therefore they have to leak it to the ground. In other words, the electron comes back to swing those charge here, and this flow of the charge between the aluminum electrode and the ground, as you slide this top PTFE apart, give you one current. Until fully displaced, no current flows. When you close, and this triboelectricity occurs again, the electron flows back in, repeat the positive charge to balance the field. So you slide this back and forth, you produce an AC output. The advantage of this one, only one electrode, one moving part. This part can be a freely moving part to accommodation applications. You can have a vehicle or walking person. You cannot have an electrode, a wire attached to the person. So this is a single electrode mode. The fourth mode is so-called the free-standing triboelectric layer. Okay. If you have two electrodes built below here, on the top of the layer here, and these layers already have a charge built on the surface here, and this layer can free slide in between the two here as you draw the cross-section image here, and this is the triboelectricity origin on the surface. There's an aluminum electrode, there's another aluminum electrode, and this is the FEP film here. If the FEP film moves to the right-hand side here, because they destroy the symmetry of the charge has to flow to here and to balance the local field. So when you fully overload this one, whole charge transport from here to here. So in other words, from here to here. When you slide back here, the charge flows from this side to the other side, again, to recover to original shape. So this sliding back and forth, because the trouble charge remain on the surface for a very long period of time. And this sliding doesn't need physical contact and back and forth. For many sliding with direct contact, so that's what we call freestanding triboelectric layers, which have a minimum friction but have a very good power output and make this kind of induction process possible without producing additional heat or consume additional energy because of the physical contact. So this is called a free-standing triboelectric layer design, and there's normally a gap between the FEP layer and aluminum, which is freely sliding back and forth. So we only have four modes: vertical contact separation mode, lateral sliding mode, single electron mode, freestanding triboelectric layer mode. All these four modes can cover almost all the mechanical action in our daily life. Let me show you a few examples. Power source for wearable, stretchable, or mobile electronics. If you use polymer materials, you can fabricate a generator like this, and this can have a physical contact separation. No magnets, no coils, which can convert. You make a shoe insole here, which convert mechanical agitation energy into electricity, and this can drive the light, and also can have wireless signal transmitted many meters away. This is from a cell power system built inside the smart shoes or intelligent shoes based on this triboelectric nanogenerator. Fabric, we can use fabric to make a triboelectric nanogenerator because we can use almost literally any materials. Use the fabric material to make a flexible battery. So this can form a system. Here is the battery. Underneath the arm is the generator. And here is the heart beating monitor system. Generate power, store the lithium battery, and drive this heart beating monitor here, send signal wireless to cell phone. So when the student runs, his heart beating behavior is being transmitted wireless to the cell phone, and this is the platform to reach the outside world. So this is a local net for individual person. Again, self-power system integrated with cell phone-based data transmission platform. We can make this fully flexible, foldable, polymer-based materials. Use this grading structure here. We can reduce the output voltage and increase the current. Using like this structure here, you can see that we be able to lit up a light here. You can see the light is the luminescent light, and it's the glass here. You can illuminate like that. This device here can produce about 0.7 watt of power and efficiency of almost 30%. And this is have a power output density reach up to 300 to 500 watts per square meter. And this again is use organic materials and gradient structure. We can also do this on the cover of a cell phone. You slide the cover back and forth. You can charge a cell phone here. This is a typical cell phone cover, and this is the we made fabric here. If you slide this cover back and forth with triboelectricity, we can generate power. As you can this example here, and this sliding back and forth. You can see those luminous light flashes as you sliding this back and forth here. Okay? So this is the charging cell phone. Power source for medical devices, particularly self-powered medical devices, or pacemakers, for medical surfaces is important. We can integrate our triboelectric nanogenerator with a rectified circuit to drive a simulated pacemaker. This is a small rat. Okay, it's a small rat. Use the breathing of the rat. We can harness the energy. We can drive the simulated pacemaker. Once breathing 3 times can drive the pacemaker once, which this is small animal. With larger animal, we can drive this multiple times. Utilize this strategy. So this is the first demonstration of triboelectric nanogenerator for convert human muscle breathing generate electricity for pacemaker purposes. We can also use fabric, and this fiber, 2 fibers can treat differently. One can give electron, the other can gain electron, and have some electrode design here. One entangle them together here, and when you have physical motion between the two, they definitely have sliding or contact. So the contact, the distance change, or rather the sliding, must generate surface charge here. This will give you a substantial voltage and power to drive a sensor. For example, this is a temperature sensor, and you can swing this generator inside this lab coat. As you see that, when the lab coat wobbling here, wobbling the lab coat is driving the fibers generate work. Then you can drive this temperature sensor here. This temperature sensor measure room temperature at 22 degrees C. Then you wait, and the student put this on the arm. The temperature will rise, the body temperature rise. Then you can see that the now still show 22 degrees C because no power supply. You wobble his lab coat, supply power 32 degrees C. And wobbling again, 34 degrees C. This is a self-power system for temperature measurement, and can be a typical example for many sensors from Internet of Things for other applications. Power source for portable device and environmental protection. We can design a small wind trigger. And this little tunnel structure here, if you blow the air through here, and then this whistle structure here is cause this tunnel to wobbling back and forth. This wobbling causes contact separation. On the wind driving, you have the turbulence. This can have a resonance here, and this is the case. You can see this little tunnel structure highlight here. The air flow through here. You can introduce surface different nanostructure here to enhance the performance here. As you see here, this is the blow through the whistle here. You can see the light flash like that, and you can blow through this one, an exit sign here. So this is the tiny range, small hole generator, wind generator. It's completely different from the traditional wind generator. Vibration, you put on this car engine here, harmonic oscillation here, drive this contact separation. This can monitor the condition of the car. You can put this on the sofa, or you can put this on the desk. These things can give you this kind of for monitoring the system, and also use the vibration of the desk, generate electricity. Again, this gives high voltage output. Just simple knocking can immediately lit up those lights. So this is the vibration sensors power generator. You can do this one as a robust structure here. This is sinusoidal structure here, and this have a very good power robustness, and it can work for a very long period of time without failure. So this one is the device made like this, and This again utilizes contact separation and a sliding mode both in one. As you can see here, this is the cover the generated by a little blanket, and then the foot stacking lit up many LED lights simultaneously. So this is the conjunction modes, triboelectric nanogenerator. Sonic wave can drive. How the sonic wave energy is very difficult. And we use two pieces of paper separated by a small gap distance. On the triggering of the sound wave, vibration occurs because contact and separation constant. Those holes are introduced to make sure the sound wave can transmission through, and also the airflow to optimize the performance generated here. As you see here, this completely almost looks like paper-thin structure here, and you can see this one can give you a sound wave harvester here attached to cell phone. Attached phone here, the talking of the student can drive this generator and can charge the capacitor. This is the capacitor, you can charge over here. So this is an example showing you use a sonic wave, you can collect the power, and this can have applications on many things. Lastly, energy efficiency, conversion efficiency. Mechanical energy agitation, particularly low frequency, causes many residual vibrations. And each residual vibration can generate electricity. If you only apply the first cycle of energy generated, it's called instantaneous power conversion efficiency. If you collect all the power generation, all this residual vibration, they call the total power generation. The total power generation from our triboelectric nanogenerator can reach up to 85%. 85%. And any small motion here, and all this kind of walking, pretty low frequency residual vibration can give you electricity. This is called total energy conversion efficiency. In our last few years research, we raised the output power density per unit area from very tiny 300 milliwatts to 500 watts per square meter. We raised the total energy conversion efficiency to 85%. The instantaneous energy conversion efficiency can be 50%. If you use liquid metal, it can reach 70%. So all this conversion efficiency is very exciting for use organic materials for this kind of energy conversion. So look at the long term. We even build a roadmap for nanogenerator applications. We focus on small power source for low consumption devices, working as active sensors, and so powered sensors integrate with current technology, so power system integrate with current technology, with new nano devices, and continue to mega scale energy need. So therefore, as time progresses, we slowly demonstrate all this kind of application here, and we still have a long way to go, but we anticipate as time progresses and worldwide more effort focused on this area, more people interest in the area, this can generate many things to come and which can benefit our life in the near future. We can charge a storage system, not only as a generator. We can integrate a supercapacitor with our triboelectric nanogenerator to have a self-charging power unit to serve as a power unit to drive some electronics. We can also integrate a nanogenerator with a lithium battery to build another self-charging power unit. This is a unit. It charges the battery itself by half the mechanical energy from the environment. We also can have built systems, for example, can half the energy because our living environment is random. Frequency random, amplitude random. But if you half them, use our power generator convert to pulse, output power. Use a power management system, we can store into capacitor or battery. Then the output will be regulated. We can drive conventional electronics, for example, the electronic watch, a scientific calculator, or car door opener. And this is the car door opener. We show you this example here. The car is located right here. this is the generator. The hand pressing generate power, and use our homemade rectification circuits and power management system. We charge this capacitor, and then the car key opens. Maybe yard away, you can see this car door opens. The light flashes. The light flash means the door is open. Total beyond the power generated by the human body motions here. So this is a demonstration of self-powered system and self-powered power management system which can drive existing electronics in a regulated and maintained freeway. We not only look at the small energy, but we look for large-scale energy. We call blue energy. Why do we call blue energy? Let's look at the large-scale energy. 1831, Faraday invented the electromagnetic induction, this important physical mechanism. Many years later, they built this generator. Today, you can have this gigantic electromagnetic generator, which is the basis for all today's power conversion from wind, hydraulic, to thermal or even nuclear, which is the basic technology. This have two components required, magnets and coils. So normally it's very heavy. It's very heavy and also costly. Look at blue energy is the energy in the ocean. 75% of the surface area of the ocean being covered by water. This water energy is gigantic. But use electromagnetic, you can use this rotation, the stream here, which ignore the dynamic surface process here. You have to have a stream or put on the floor of the ocean or use this floating back and forth to get out this energy. But in any case, if you build this one, it is expensive, engineering difficult, and bulky and lower efficiency. Make this kind of blue energy almost impossible. We invented our triboelectric nanogenerator focus particularly on human small-scale motions, but we can target at this one. I'd like to present a blue energy ideas. How do we do that? We have 4 modes: contact, separation, sliding, single electrode, and freestanding triboelectric layer mode. So all these modes can combine together, become a unique energy technology for small scale and large scale. How come you do large scale? Let's give you an example here. We can use this contact electrification liquid and the polymer. This is the water contact with polymer surface can cause triboelectricity. If you have 2 symmetric electrode built underneath here, if you have water surface rising here, the water is naturally charged. This destroys the symmetry of the 2 electrodes, so the electron flow from here to here to balance this field. If more water soaking the surfaces, more electron flows, and the flows here, this flow of electron is a power generation. Until this fully covers the surface here, no more current flow. If the water descending here destroy the symmetry again, the electron again in the flow. So this cycle motion, so if you see the water level rises, descending, rising, descending, this current can generate as an AC current, follow this one. Here's a simple demonstration. This is the basket. Basket have our generator right here, and this will have water here. You can see the water level here. This is the blue basket here. And this, if you walk into this basket, the water level emerging the surface or descending here, you can see the light flashes. Use small contact electrification with water and polymer materials. Even you have a shower head here, this can generate power as well. This shower, this is similar to like the rain. You shower at the triboelectric nanogenerator, all this thing can happen. This can use for harvest energy from raindrop, from the water level, water surfaces, and any kind of contact between a liquid and a solid. So this was the beginning. We look at what for energy generation, different from the hydraulic rays here. But if we look at the ocean here, this low frequency, irregular, massively distributed power is what we need to target at. But use classic technology, this is almost impossible. How do we do that? If we build our nanogenerator inside a small ball, like a baseball, connect all of them into a net, this net can put in the water, and as the water floating up and down, this net floating up and down. This uses mostly organic materials, so they are light, they float on the surfaces. And this floating on the surface can generate power. This is the net idea, like a fish net idea. Only the fish, the node is made of triboelectric nanogenerator here. And this mass is distributed on the surface here. And this idea was first published in the Faraday discussion in this article. So this is called blue energy, and energy could be on green energy. This is possible. Our group has done the work. We can fabricate this device here. We can put it in water as the floating water, and this can generate. If we extrapolate this idea and do the calculation, we find that it is possible, and theoretically, we can generate over a megawatt power per kilometer square of the surface area of the ocean. Those can be shallow waters or can be deep water. It doesn't matter because it's only use the dynamic on the surfaces. So we can use the remote areas and the deep ocean for power generation. And recently, we can do this in the bores here. The bores is fully sealed, so no water infiltration here. And so that can be protected with inside generator. Outside can be anything, can grow anything on top, it doesn't matter. Contaminate, it doesn't matter. As long as this floating water here is a live flashes. This live flash will give you over 100 volts. This little sphere give you over 100 volts, which for the same volume is impossible to use electromagnetic generator. Ours, due to the high voltage, have a unique advantage, particularly at a low frequency, is unreplaceable, unbeatable for harvesting low frequency, large scale distributed water energy, and this is the structure of the spheres we fabricate here. Again, the idea use this one to build a net so that we can be focused on large scales here. But this each individual unit is constructed as such. So as a summary, we demonstrated several things. Number one, we show the triboelectric nanogenerator. Use the well-known triboelectric effect. We can focus on solar-powered systems, solar-powered sensors as well. We also can focus large-scale blue energy, which the energy we target at in the next near future. So I hope that this gives you a good introduction of our triboelectric nanogenerator as micro nanoscale generator, but also a generator which can for blue energy, and energy can be possibly a future for the world need in the next many years to come. Thank you.